Welcome guys to my channel. This is Chemistry with Min. Today
Today we'll be discussing nuclear chemistry.
There are a lot of negative connotation when you hear radioactivity and nuclear.
Did you know that nuclear energy has a lot of uses? One of the most commonly used usage of radionuclide is to diagnose different diseases such as cancer.
Radiation is also used to eradicate tumors. What are the radioisotopes used in vivo? Well, some of the radioisotopes used in vivo are xenon 133, technetium 99M, iodine 131, iodine 125. Whenever we hear nuclear, we imagine war or nuclear bombs, mutations, and other genetic deformities caused by radiation, hair loss and infertility, sickness, and death. Can also be used in food preservation. Radiation can extend the shelf life of a product without sacrificing the quality of the fruits and vegetables. In return, having a safe and consumable items in our market. In addition to that, we also use radiation to eradicate pests such as mosquito by making them sterile. In addition to that, radiation can also eradicate bacteria to make our place more sterile. Moreover, nuclear energy provides a efficient form of energy. It can also make the cost of electricity more affordable. Nuclear energy can also provide a clean source of energy. And lastly, a safe form of energy provided it is managed properly. Let us go inside of the Bataan Nuclear Power Plant here in the Philippines.
All right, what's the difference between chemical reaction and nuclear reaction? In chemical reaction, atoms are arranged by breaking and forming of chemical bonds, while in nuclear reaction, elements are converted to another element. Only electrons are involved in chemical reaction, while in nuclear reaction, proton, neutron, and electron and positron are involved. In chemical reaction involves absorption and release of small amount of energy, while in nuclear reaction, it involves a large or intense amount of energy. And in chemical reaction, rate of reaction is affected by surface area, concentration, temperature, pressure, and presence of catalyst. However, in nuclear reaction, it is not affected by those factors.
December 1895, William Conrad Roentgen discovered the X-ray. And in the picture on the right side, it's one of the first X-ray ever performed, and that's the wife's hand, as you can see here.
1896, the first medical use of X-ray was performed. In 1896, Antoine Henry Bertel discovered radioactivity emitted by radium compounds. In 1898, Pierre and Marie Curie isolated the radioactive elements polonium and radium. The atom is the smallest unit of matter. Atoms combine together to form molecules. And the structure of atom, we have proton, which is a positive charge, electron, a negative charge, and neutrons, which has no charge. To get the atomic mass, you need to combine neutron and proton in order to get the atomic mass. The atomic number is equal to proton and electron. So, if the atomic number is 4, proton is also 4, and electron is also 4.
How many neutrons, protons, and electrons are in the nucleus of the following? Let's try to answer this problem. Okay, remember from the previous slide that atomic mass is equal to proton plus neutron. And the atomic number is equal to proton, and proton is equal to electron. Now, let's answer this. All right. So we know that the atomic number is 11. So, and we know the equation is atomic number is equal to proton and proton is equal to electron. So proton would be 11, electron would be 11. Now, we are missing the electron. Remember the formula, atomic mass is equal to atomic number plus proton plus neutron. Okay, here's what we're going to do. We have to move the proton to the other side. So our equation will be atomic mass minus proton is equal to neutron. So that would be 12. Very good. So let's answer this, another problem. We know the atomic number is 54. So the proton will also be 54. Electron would also be 54. Okay, what would be the atomic mass? It's 131 minus 54. So we got 77 for the neutron. Next, we know that the atomic number is 74. So proton is also 74 and electron is also 74. Now, electron is still missing. So 184 minus 74 equals 110. That would be our final answer.
Isotope is elements having the same atomic number but different atomic mass. Isomer is identical elements but different nuclear energy states. Isobar is elements having the same atomic mass but different atomic number. Isotone is having the same neutrons.
All right. Let's identify if it's isotone, isobar, and isotope. Remember what we said in the previous slide. Isotone, same neutron. Isobar, same atomic mass. Isotope, same proton. All right. All right, let's do this. So number 1, we have this problem. Is it the same isotope, 6 and 7? No, it's not the same proton. Same atomic mass? Yes. See, they're both 14 in the upper part. So this is isobar. How about this one? Are they the same in atomic mass? Nope. Are they the same in the atomic number? So they are the same in the atomic number. So this is isotope. How about this one? Is it the same atomic mass? No. Same atomic number? No. And therefore, this is isotone. How about this one? There are both 2 in the atomic number. So this is isotope. This one, both are 40 in the atomic mass. So this is isobar. Alright.
If Coulomb's law on electrostatics dictates the force of propulsion between two like charges, such as in the case in the nucleus of an atom, but why does the nucleus doesn't fly apart? It is because of strong nuclear force. How to determine the stability of an element? So there are 4 ways to determine the stability of the element. So first, the ratio between neutron and proton, the pair production, the magic numbers, and isotopes with atomic number greater than 83. So let us begin. So neutron to proton ratio, if neutron over proton is equal to 1, then it is stable. However, if it's not equal to 1, then it is unstable. So if neutron over proton is greater than 1, you need a beta decay to stabilize it. If the ratio is less than 1, then you need a positron emitter to stabilize the elements, okay? Second is the pair production, okay, moving on. So if both proton and neutron is odd, then it's the least stable. If only one of them, if proton is odd or neutron is odd, then it's less stable. But if both are even, then it is highly stable. All right, let's move on to the magic numbers and isotopes with atomic number greater than 83. All you need to remember that all noble gases are stable and all numbers greater than 83 is unstable. So alpha decay is the most common to have an atomic number greater than 83. So remember that, okay? Activity. It is the spontaneous emission of energy from an unstable atom. There are 2 types of radioactivity. One is natural, which is found in nature, such as uranium and plutonium, while artificial, which is made by man, such as technetium and actinium. 3 types of radiation can be emitted: alpha, beta, gamma. So in alpha particles, it's nucleus of helium, which has 2 protons and 2 neutrons. While in beta, it's an electron, and gamma, it is an electromagnetic wave. So the heaviest among those 3 is the alpha, and the lightest is gamma, which has no mass. So
alpha particle is the slowest, and, and the fastest is the gamma ray. And then the ionizing effect, the strongest ionizing effect is alpha particle, and the weakest is the gamma particle. It is the alpha particle is dangerous inside. Moving on, as you can see in this diagram, you can see alpha particle doesn't reach too far in our body compared to the gamma ray, which is the most penetrating among the three. Alpha particle can be stopped using our skin or a piece of paper. While in beta rays, beta particle, you can stop it using aluminum, and gamma ray, you, you need a thin sheet of lead or a thick sheet of concrete in order to stop the radiation. Radioactive decay is the release of radiation by radioactive isotope. So we have alpha decay, beta decay, and gamma decay. Let's figure out how does it function, okay? Alpha particle is consist of helium nuclei with 2 protons and 2 neutrons. So basically, the loss of alpha particle, which is the helium nucleus, as you can see in this diagram, you have uranium-238 and it decays into thorium and helium. What can you see in the picture? They are both balanced. What's the atomic mass? 238. And in the product, you have 234 in thorium and helium-4. So if you add them all together, helium plus thorium, you get 238. And in the uranium, you have the atomic number 92. And in thorium, 90 and helium 2. If you combine helium and thorium, you get 92. So just remember, the left side, which is the reactant, and the right side, which is the product, must always be equal in both atomic mass and atomic number. Moving on. Beta decay is a high energy electron with a -1 charge. So basically in beta decay, it is a loss of beta particle. As you can see here in this diagram, you have 131 iodine, which is decayed into xenon and an electron. As you can see, they are both equal. So as you can see here, you have 53 in the atomic number, and the xenon is 54, and the electron is -1. So if you combine that two, you will get 53. Did the atomic mass change? No. As you can see here, it's still the same. A positron emission is a process in which a positron is ejected from the nucleus, and in the process, a proton is converted into a neutron. So as you can see here in this diagram, the mass stays the same in the nucleus while adding a positron. In electron capture, allows proton turn into neutron. As you can see in the picture, you have potassium 40, and it ejected a electron, which turns into 40 argon. What you can see here, it's balanced.
you have 19 plus -1 on the left side and 18 on the right side. So perfectly balanced. Gamma ray is a high energy form of electromagnetic radiation without charge or mass. Gamma ray typically doesn't occur alone. Usually it occurs with beta or alpha. The loss of gamma ray, high energy radiation that almost always accompany the loss of a nuclear particle. Nuclear transmutation, a process in which one nucleus is transformed into another through bombardment by various subatomic particles or ions. Nuclear transmutation differs from radioactive decay in that the former is brought about by the collision of two particles.
Let us try to balance this nuclear equation. Okay, so we have this nitrogen, we have 30 nitrogen as per the atomic mass and 7 for atomic number. So we want to balance it. So what can we do to make this still 13 in the atomic mass and change this into 7? So we must do positron emission. So this is with E 0 plus 1. So is this equal? Yes. Let's try another one. What equation? What can we do to make this balance? We have the same atomic mass, both 11, but this one is 1 lesser than this number. So we need to do electronic positron emission. Here you go. Is it balanced? Are they both 6? Yes. Are they both 11? Yes. All right. So what shall we do here? What element is missing to make this equal to the copper? So we have 61 for the atomic mass and then 28 for the atomic number. Remember, 29 minus 1, 28. Now, let us look for the periodic table. What's the 28th number, 28th element in the periodic table? So that would be nickel. All right, let's try another one. So we have 21 and 11 here. So nothing will change in the upper side, as you can see here. There you go. 21 there. And then we need to subtract 1 since this is plus 1. So this would be 10. So what's the 10th atomic number? That would be neon. All right.
What is the difference between nuclear fission and fusion? Nuclear fission is a process in which a heavy nucleus split into lighter ones, generating one or more free neutrons because a heavy nucleus is less stable than its product. This process releases a large amount of energy. Nuclear fusion is a process in which two light nuclei combine to form a heavier one. If two light nuclei combine or fuse together to form a large and more stable nucleus, an appreciable amount of energy will be released in the process. What is half-life? Half-life is the amount of radioactive material, A, compared to the original amount, or any quantity which is
proportional to A, or the original amount. Okay. So here's the important formula for half-life. So NT is the ending amount, N0 is the initial amount, lambda is the decay constant. You can get the decay constant by ln of 2 divided by the half-life. And the T is the elapsed time. So in equation number 1, you will use that when you want to figure out what's the final amount in a certain period of time. While in the second equation, you want to find out what's the original amount. And in the third equation, you want to find what's the half-life of the substance. And in the equation number 4, you want to find the time elapsed of the object. Why do I need to know about half-life? Does it really matter? Well, of course it matters. One of the usage of half-life is carbon dating. Carbon dating is a measurement of the beta decay activity buried of a piece of wood or any artifacts such as fossils, provided a measurement of the time elapsed since it was living and it equilibrium with the atmosphere. Knowing about half-life is important because it enables you to determine when a sample of radioactive material is safe to handle. The rule is it needs to be in background radiation level or it occurs 10 half-lives later. All right, let's try to solve this problem. So, what is the half-life of a 100-gram sample of nitrogen 16 that decays to 12.5 grams of nitrogen in 20 seconds? So, we have this formula. So, we're missing the half-life. We have the initial sample, which is 100 grams. Then final sample, 12.5 grams. And time elapsed, 20 grams, 20 seconds. So we need to find out how to get that half-life. So we need to retain this. All right. So let's divide initial time equal to NL time. So we need to remove the E. So let's have the ln here, ln here. So we'll get nn 0. So this will be cancelled out. Then we have time. So let's divide time. ln 0 over time. Now let's substitute the values. So ln, so this is 12.5 divided by 100 over 20 seconds. So let us get our calculator in order to solve this. All right, let's have our calculator. calculator. Alright, let's wait up to load the system. Oh yeah, I forgot the negative sign in the upward. Sorry, I forgot here. Negative. Sorry. This is also negative. 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 All right. So the answer would be 0.10. But is this the final answer? Not yet. Remember, this is just the rate of reaction. So ln squared divided by, sorry, half time divided by 0.10. So ln2 divided by 0.10, that would give us 6.9. That would give us 6.9 seconds. Alright, let's check. That would give us 6.9 seconds. So that's the half-life. Alright. So remember half-life. So if this is 100 original and then the second would be 6.9 seconds, would make it 50 grams. Then gram, okay, 25 grams would be 13.8 seconds, 12.9, oh sorry, 12.5 would be 13.8 plus 6.9, that would be 20 seconds, 0.7. So it's near. So it takes more half-life in order to get this. Let's try another one. Alright, let's try another problem. Iodine 131 has a half-life of 8 days. If there are 200 grams of this sample, how much of iodine 131 will remain after 32 days? Alright, so let's determine the given. We have the half-life, which is 8 days. Initial amount 200 grams. Time elapsed 32 days. And then missing final thing, final substance. So we have this equation. We'll use this equation. There you go. There's negative here. All right. So don't forget the E. Okay. That's our equation. So in order to get this, the activity rate, so ln2 divided by the half-life. So let's do this. ln2 divided by 8. So let's do this. ln2 divided, sorry, ln2 divided by 8. So we got the activity is 0.08. Now, let's substitute everything. Alright, let's substitute everything. So, N is equals to 200, E negative 0.08, and the time is 32 days. Now, get a calculator and solve this. So, E is equal to 0.08 times 32 times 200. Alright, sorry. Alright, E is negative 0.08 negative times 52 7 times 200. So the remaining will be just 15.6 grams. And that would be our final answer. Binding energy. It is the energy required to separate a nucleus into its individual protons and neutrons. So, remember Einstein's famous equation? We will use that. And that's E equals mc squared, where E is the binding energy, m is the mass deflect, and c is the speed of light. Alright, let's try to solve another problem for mass defect and binding energy. Alright. So first step, identify what is proton and neutron. So we have 5 proton and 5 neutron. So to get the mass defect, so 5 proton times 1.007 U there plus 5 neutron, there you go, times 1.008 U. There you go. So now let's multiply it. So 5 times 1.007, that would be 5.035, and then 5 times 5, 5 times 1.008, that's 5.04. Now let's add the two of them. So 5.035 plus 5.04 is equal to 10.075. There we go. That's our mass deflect. And then let's subtract this into 0.019 minus 0.075. 0.0129 minus 0.75 will have 0.621. Now that we have our M, let's get the binding energy. So remember this formula. So remember, C2 is equal to 931 MeV over U. So let's just substitute the value. 0.062 times 9.1, 931 MeV U. So the binding energy is 57.81 MeV. And that's our final answer. Okay, let's try to solve the binding energy. So we have 17. The atomic mass of oxygen is 17 and the atomic number is 8. So if oxygen has 8 protons and 9 neutrons, what would be the mass deflect and the binding energy? So in order to get the binding energy, first step, we need to know what is the mass of protons and the mass of neutrons. So the mass of protons, so we have 8 protons, we'll multiply this by 1.0072 plus 9.008 and then add them together. We'll get 17.13 6193. And then, in order to get the mass deflect, so we'll need to subtract this by the atomic mass. So, mass of nucleons, this one, minus the atomic mass of the original one. So, that's 17.004. So, the total mass deflect is this. And then we need to convert this into kilograms. So in order to convert this to kilogram, this one here will multiply to 1.66 times to the negative 27 in order to get the kilogram. Then let's substitute everything to this equation. Remember this equation. E equals mc squared. So multiply that and we'll have the final answer here. But if you want to convert this into binding energy in this unit, you need to divide this by 1.6 times to the 10 negative 19. So that will be our final answer if you want this unit. There are 3 radiation protection principles, which is time, distance, and shielding. The less time that you spend in a source, the less radiation you will receive. And then, if the greater the distance from the source, the less radiation that you will receive. Or if your distance is nearer to the source, the more radiation that you will receive. And lastly, shielding. So if you're behind a shielding from a source, less radiation will be received. For example, if you have a gamma radiation source, you need a lead shielding in order to protect you. If you have an alpha source, you just need a piece of paper or plastic to shield you. Why do we need to detect radiation? For research application, environmental safety, power regulation in nuclear reactors, personal protection of occupational workers, estimation of radiation dose in treatment of patients, and calibration of radioactive isotopes. So how do you manage nuclear waste? For low levels of nuclear waste such as contaminated equipments, materials, and protective clothing used in the hospital and industries, you need to put the contaminated equipments in a drum and surrounded by concentrated and put it in a clay linen landfill mines. In medium level, components from nuclear reactors, reaction or radioactive sources such used in medicine, practice, and research are some of the example of medium level category of nuclear waste. So basically, they are mixed with concrete and put it in a drum, stainless steel drum in a purpose-built storage. And then lastly, the high-level nuclear waste, which is one of the example is using nuclear fuels and chemicals from processing plants. So they are stored underwater in large pools for 20 years, then placed in a storage cask in purpose built in underground storage. Okay.
Power plants and research reactors in a safe and secure way. Waste containing only radionuclides with very short half-lives can be stored for a few days or years to allow for the decay of the nuclides. This type of waste is usually generated when radioactive materials are used for research or medical purposes. Eventually, it can be disposed of as conventional waste.